So hello everyone. In this lecture I will discuss two questions and also discuss their solutions from real analysis. So here is the first question 1. Suppose you have a real number x, then show that there is an integer m such that m is less than equal to x less than m plus 1. Moreover, show that there exists an integer l such that x is strictly less than l less than equal to x plus 1. Okay. So let's try to figure out at least the first one by the picture. Suppose you have this real line, okay, and you have x somewhere. If x is x is an integer, it belongs to, let's say, first of all, then I can choose m equal to x. Automatically this will be satisfied, right? But if x is not belongs to z, for example this case, then here I will collect all the integers which are below x or equal to x. Okay, so basically this set. Then of course this set is non-empty because there are a lot of integers below x, right? So this is a non-empty set, and I will take the maximum of such integers. Okay, that is one number, and that maximum is also belongs to z, right? And by definition that is less than or equal to x, and since this is the maximum with this property, right, which is in z, since m plus 1 is also in z, so that has to be outside this set because this is the maximum of this set, right? So automatically this is true. So this is the proof of the first property. Okay, now what about the second? In this case I will collect all the integers which are above x. Okay, so when k is belongs to this, k is above x. Okay, and I will collect again this set is not because there are infinite such k which belongs to z. Now I'll take the minimum of such k's. Okay, so minimum automatically k is strictly that minimum l is automatically bigger than x, but since this is the minimum, if I take x plus 1, right, I mean that minimum is l, l is bigger than x, and that has to be always less than equal to x plus 1, right? Because I mean like l minus 1 if I do, for example, then l minus 1 is outside the set, that means less than equal to x. Okay, because l is the minimum, right? So I will get this inequality. Okay, and l minus 1 is also an integer, that's the reason, right? So that element has to be outside this set. Okay, yes, fine. Next we will discuss another important question, which is this. So let A is a subset of R which is non-empty, and let x is a real number. Then we define the distance between x and A by this d of x comma a. This is the notation for distance between x and capital A. Capital A is given set. This is the infimum of mod of x minus a such that A belongs to A. Now this question is saying if alpha is a real number which is the supremum or the least upper bound LUB of this set capital A, then show that distance between alpha and A is 0. Okay, this is what you have to prove. So if this is alpha is my least upper bound, then by the property and take any n which is a natural number, then alpha minus 1 by n is less than alpha. Then by since alpha is the least upper bound, you can always find some element an in the set such that an is in between alpha minus 1 by n and alpha. That is what I have written here. For every n belongs to n, there exists an n belongs to capital A such that alpha minus 1 by n is less than an less than equal to alpha. This says that alpha minus an is non-negative if I subtract alpha minus an from this inequality, and if I use this first inequality, I get alpha minus an is strictly less than 1 by n. Okay, so let us keep this as a equation name. Okay, 1. So by definition, distance between x and a is this infimum, right? But an is in a, and each infimum is always less than equal to each element, and alpha minus an is an element of this set, right? So but alpha minus n is less than 1 by n by 1, and this is true for every small n belongs to n. This says that distance between alpha and is 0, right? But why, right? Observe that by definition distance between alpha and capital A is always bigger than or equal to 0. So if distance between alpha and A is not 0 from here, then distance between alpha and A is strictly positive, right? Okay. So now use the Archimedean property, right? By the Archimedean property, you can look at my previous lecture for the Archimedean property. There exists an capital N which is in the set of natural numbers such that 1 by n is less than distance between alpha comma A, right? So let us give equation 2 as the name, and let's say this is star. Okay, so what star says, let n equals to n in star, then star gives distance between alpha comma A is less than 1 by n, right? Let's say this is 3, but 3 and 2 are contradictory, right? So the only possibility is that distance between alpha and A is 0. Okay, right? So this somewhat says that the distance between the supremum of a set and the set is nothing but 0, right? Okay, now I'll prove or solve one more question, which is question 3. The question is, if r is not equals to 0, is rational and x is irrational, then show that r plus x and rx are irrational, right? Proof. How to prove this, right? So how to prove this, right? So what we will do is that we'll try a contradictory argument. Okay, so step 1, here you prove that r plus x is irrational. Okay, so by contradiction, what does it mean? If r plus x is rational, right, let r plus x belongs to the set of rational number, then r plus x equals to p for some p belongs to q, and that says that x equal to p minus r. Now p is rational, r is rational, this belongs to q, since p and r both are rational, and right, but x is irrational, right, and x equal to p minus r, so we get p minus r is not irrational. So this and this contradict each other, so r plus x does not belong to q, right? So basically our assumption is wrong, right? Okay, so it has to be an irrational number, right? Okay. Step 2, here we have to prove that rx is irrational. So it's saying you have a rational number, their sum is irrational, and their product is also irrational, right? So sum irrational is already proved here. Now we'll prove their product is irrational. Again we'll go by contradiction. So by contradiction, let Rx belongs to Q. So Rx equals to Q for some small q belong to the set of natural number, a rational number, right? And that says that x equal to q divided by r, and you can divide by r because r is not equal to 0, right? R is non-zero. You can divide. Now q is rational, r is rational. So since q comma r both belongs to q, implies q by r also belongs to q. That implies x belongs to q, but x is not belongs to q given x is not a rational number. So this is a contradiction. So our hypothesis or the contradiction assumption is wrong. So Rx is not equals to, not belongs to Q. So Rx is irrational. Okay. So this proves all, this solves all the three questions, and here I will end the discussion.